there, Engine Performance Expo viewers. Welcome back again, Lake Speed Jr. from Total Seal here with Randy Neal from CWT, right?
Yes, sir. Here we are to help you out.
Most well-balanced man in show business.
Thank you for that.
So anyway, I'm really excited about this because this is something I don't know a lot about. I mean, I understand that you have to balance things, or you should balance things, but you're the wizard of all this. So I'll start us from the primer level, because I'm the dummy, and take us all the way through this process, because, you know, right there behind you is this crankshaft that we have for the Engine Performance Expo engine, and man, we want to make a lot of power. We also one day want to turn a lot of RPM, so I kind of think we're going to need your help. So tell us how we do this. Where do we begin, Randy? And well, I guess maybe the first thing is, why are we doing this?
Well, let's talk about it. Unbalance or out of balance, it depends on your phraseology, is probably one of the most misunderstood part of engine building. Now, balancing, in a nutshell, is if you had a seesaw and you're going back and forth. Well, when I was a young man, that was our high-tech playground. Now, it's not something you're going to find on YouTube anymore, but the bottom line is that if I had equal weight, equal distance, I could hover. So as a child, I thought, that's sort of interesting. And we could dangle. But if I changed my weight times distance, then of course it would change. Well, that is balancing, bottom line. I'm canceling a load on one end against the other. So now when we put it from a static environment into a dynamic environment, we have a situation where we have unbalanced weight, as I just talked about, but now we have centripetal force that's going to sit there and basically grow. It's an exponential increase. That balance is critical to getting rid of an unstable and exciting event that will cause the rest of the engine components to respond. In other words, once you vibrate, just think of a tuning fork. If you hit it, bing, it doesn't just stop. It rings out. Well, as we're spinning this engine, it's constantly being hit, so it never settles down. And the more power or the more energy, and this is bad energy, by the way, that's in there, traumatizes the entire engine. Now, balancing in its own right doesn't make power. Let's be clear on that. What balance does singularly unleashes power. That's a critical part of the equation. But the other side of it is it really does take a situation where you're getting your engine in stability or a stable platform, which gives you longevity. The tolerances we're balancing to now are 0.16 ounce inch. That doesn't mean a lot to you guys, but let's just simply say that 10 years ago, it was 2 ounce inch. Now, from 2 ounce inch to 0.6 is a substantial amount. In other words, you're about 25 grams. But the difference is these vibrations that were set off were triggering some of the engine analyzing capabilities. In other words, they have accelerometers that communicates with the electronic computer, and what it does is it sees a vibration. Well, it interprets that as maybe a pre-ignition or detonation.
Right.
So now what happens is it goes back and it fattens the motor up. So in the old days, the blocks were a lot heavier, and that heaviness, if you will, was a damper. It would actually hold us back. Now, with the thinner blocks, especially the lighter alloys, and some of the graphite blocks we're seeing now, these things are excitable. Now, changing the frequency. Changing frequency, exactly. So these accelerometers are in there just triggering. The ECI is sitting there communicating and making adjustments to the fuel. Well, the OEMs, in order to meet these CAFE standards, they realized they had to lower the first order balance. And that's what we do here. So turn down the noise. Turn on the noise. There you go. That's what I'm hearing, right? Yeah, is that essentially there's so much noise being made in the engine, so we need to start balancing some of these components to turn that noise down so the sensors work properly and have a clearer signal so that it makes the correct decisions. Now, the other side of it is that the stability is critical, because that vibration that's sitting there in the engine affects everything downstream, anything that's connected to it. But I got to get you to understand this is a key part of balance. If you leave any residual balance there, it will not get better. In other words, if it, a lot of people like to use grams as a consideration. So I'm 20 grams out. Well, guess what? That 20 grams can't magically clean itself up. If an engine was running, let's say you had a bad fuel injector, right? It shutters, it does all these things. You can clean that up by changing the injector. Or it can be an ignition wire or something like this. But balance is a constant. Now, if you don't fix it before you assemble that engine, you don't have any other options after the fact. If you don't, go ahead. I'm thinking about my go-karts and how after you mount the tires on the rims, we balance it.
Because if it's out of balance, you go on the track, the faster you go, the worse it bounces around, especially if it's your front tire. It's kind of makes it hard to drive. So I'm catching on here. This is good. So keep on going. So
well, at the end of the day, here's the biggest deal with this. You're driving on the road, you put 4 new tires on it, you're driving, it's just perfect, 60, 70 mile an hour. You run off the side of the road, all of a sudden there's a shudder. Now you got to appreciate that's what's happened is that tire, or at least one of them, has been disrupted, and it has to go through all this mechanism until you feel it. Right? So this is the linkage that we keep talking about. If there's unbalance, and I've caused this by running off the road, now you drive back on the road, hey, it's back to normal. You don't get that with the crank balance. There's no recovery.
Yeah.
You get one shot at this.
Yeah.
If you don't, you own it.
Okay.
Right?
So what's the first step, right? So we now we know we need to balance it. We don't understand the importance. So where do we begin?
One of the things that all engine builders understand is that heavier mass of any object that's being moved has parasitic loss. In other words, it's got drag. Now, if you can reduce the weight, we all understand this, we all lower our physical weights, but there's different ways to do it. Now, sometimes it's an alloy change, very simple.
Yep.
Sometimes it's a matter, for instance, a steel rod versus an aluminum rod. But some of the things that also have a relationship would be like, for instance, piston rings. Let's just talk about that change in life.
I know about those.
Yeah, I happen to know a guy who's pretty sharp on that. Bottom line is, if we were to sit there, and in fact we have a sample here, if I was to sit there and take this ring right here, this is a 16th?
16th ring,
16th ring.
4185 bore.
All right, most commonly used ring I can think of. Well, guess what? We have a new guy. Take a look at this bad boy.
Also a 4185 bore, but that's a 0.5 millimeter ring out of a NASCAR engine. I won't say whose, but I may know a guy.
Here's the biggest thing. The weight mass, this is 16 grams. This is 13, well, actually 16 and a half. This is only 3.
Yeah.
One-fifth the weight. Now, you got to understand as the rotating assembly is what we call the reciprocating side of it. Number one, moving lighter objects, instant power. All right? In other words, you have the advantage of not having this excessive amount of energy that has to be controlled. Then you go to drag. Now, this is really where this guy's expertise is. So
the weight part of it to me is the fascinating part, actually. And like you said with the balancing, that the mass here is so much less than the mass there. This is easier to control because this has to stop, start, accelerate, turn back around. Every single cycle, it goes from mean piston velocity, which can be really fast, and feet per second, to a dead stop and back. That change of direction, that inertia, there's way less inertia in this. This is easier to control. Why we have lighter valves? Well, it's the same thing. Big piston rings, heavier, and now obviously with the balancing part, that weight of that ring factors into the job, right?
Absolutely. In other words, when we build the bob weight, this is just one part of the equation. We have the rings, obviously, and it goes to the entire assembly, by the way, but everything that's moving, if you can lighten it up, just perfect. It's actually going to sit there and unleash power. Now, the sealing side of it, again, that's the expertise over here. We're talking about the energy being contained. And I will simply tell you, there's one of the key factors here is that with this assembly, lighter, you're going to make more power. Now you say, wait a minute, you told me balancing didn't make power. No, sir, it unleashes power. Right. That's the critical part. Because
the power is actually made in the combustion event.
Absolutely.
And how much of that actually gets to move the part, again, it's back to simple physics. It's easier with a given amount of force to move a lighter object.
Yeah.
You can accelerate it faster. That's why race cars, crew chiefs, light, low, and left. That's what you want, at least in NASCAR. You want it on the left-hand side, but you wanted it light and low, so you have that low center of gravity, and if the car is lighter, it's power to weight ratio, and that's kind of what I'm catching on here. So I'm learning something, Randy.
Well, listen, the bottom line is light is good. Structural integrity is better. Now, we got to talk about that in the sense that when we make these things, this bad boy right here can seal better than this guy.
Because it's not a structural component.
Right, so this is the deal, is that we have an opportunity here to move us to the next level of technology. I just came out of a facility that is doing thicker rings, in fact, on their rebuilds, and they're saying they don't have a long life in them. I said, really? I said, let me put it to you another way. And I know, Lake, you did this a while back. You did a simple test where you decreased the ring size and running on your mule dyno. What did you see there?
Oh, besides the 20 horsepower, we saw 30-degree reduction in water temperature and oil temperature.
That's critical to longevity.
Yes.
Let's be fair with this. No engine likes to be on the high side of its temp band.
No.
So one of the key advantages, again, right here, temperature. Ceiling pressure, it can do it. I haven't seen anything that says, and by the way, in the old days, I'd go into a heavy-duty shop and say, nah, it can't work. Well, they were wrong.
Yeah.
And that's what the industry is all about right now. We're taking all of the old perceived ideas that we thought were absolute, and we're opening up the door with this. Now, balancing, where does this go to the next level? Well, we're actually going to have to take all of these components down, we're going to weigh them up, and we're going to build a bob weight card. From there, we're going to attach the bob weights to the crank, and we're going to spin her up, and we're going to find out just what the offending mass is and what it weighs. Now, that's a little unusual.
Offending mass sounds scary to me, by the way. It's like, oh, I'm sure I want to see that.
Well, actually, it's a good way. I try to use some words sometimes to get people's attention. You got to understand, when you're balancing, you have to remove the offending mass. Now, remember, the seesaw event is just clear as bell. In other words, if you have equal weight, equal distance, single pivot, cancellation is what balancing is all about. So we do have an issue, though, that we want to make sure that when we do this, we try to achieve what's called a couple. Now, a couple is simply that I have a force going this way and a force going this way, 180 degrees. And by doing so, the load, whatever this is up here, I'm going to use grams for a minute. 10 grams here, 10 grams here. But when I go to the center of the crank, it's 0. And that's if they're a perfect 180. So by lowering this, and in other words, if you sat there and you spun this thing, it would actually do this, a bicycling effect. But the more unbalanced, the larger, the higher the gyration, bigger and bigger. Well, what we want to do is come down to this guy. Right here. So when we don't have offending masses, or we do have offending, depending upon your perspective, I need to cancel it 180 degrees from there. That's
okay, because in some cases, right, with the way the throws of the crankshaft are, you can't eliminate the offending mass. So if I can't eliminate it, I got to cancel it.
That's exactly right.
See, catching on here. See, look, chemistry guy here. I like balance. I understand chemical balance. Super important. Catching on that it's not just chemistry that needs to be balanced, is everything else in the engine needs to be balanced.
Absolutely. Listen, this is really as basic as it gets. For some reason, people want to put voodoo into it. So what we do here at our facility is we take the voodoo and we get it out of it. This has always been a science since day one. Now, the equipment that we had in the old days, little mental interpretation. So out of that came the voodoo. Those days are gone. You know, you just forget that. Now we have the equipment, we have the ability, the electronics, the software, that, quite frankly, when we train people, we tell people if they run a touchscreen screen at McDonald's, they're overqualified now. That's how simple it's got.
Just tap, tap, tap.
Tap, tap, tap.
Go. Well, cool.
All right.
So let's make some parts, huh?
Let's do it.
Awesome.
Let's go ahead and just get a quick bearing set. I'm going to take that. I'm just going to bring this in real quick. And I'm going to go ahead and enter that. So we sent that to the computer. That's done. May as well put the locks here. In this case we have 2. And I'm going to put in locks. Here we go, 2. And print. So again, we log that in. Alright, take those away. Now we're just going to do pins. We'll do this rapid. Pins. Alright, so we'll do pin. So that's number 4. Okay, now let's bring those here. We'll go to pistons. Okay, pull that out. Now we're going to take rings. Alright, we'll re-enter that. Now we're going to go to our rods. Alright, we're going to enter. I did not pick it up. There it goes. All right, that's what happened before. Okay.
Okay, so we weighed all the parts. And Randy, this software you've got is super cool. So essentially, as you weigh it, you push a button and it just goes straight into the bob weight card.
That's correct.
And it calculates out and tells you basically how much weight to hang on this thing.
Well, yeah, it's important that we have the weights and they're equal on each half. One of the things that's unique about our bob weights, they're moment match centered. And what that simply means is, I'm just going to grab one here, is once the units are put together, regardless of where they are in rotation, the load moment is always in the center. So it's critical that these things are made, and we do on CNCs, but we have equal mass, 180 degrees. So the guide pins maintain the alignment, and we minimally torque them so there's no distortion.
Got it.
Right? So in this particular case, we're doing an adjustment. We've already roughed this in. And so what I'm going to do here is I'm 864.1, and we'll go ahead and we'll put a half gram on there.
And you need to be 864.5.
0.5. Son of a gun. There we go.
Look at that. How about that? Like you prepared for it or something.
Yeah. So at the end of the day, we will take these units, and we always go from big, and you'll see their male-female relationship so that they locate.
Okay.
And then, of course, we'll come back with our final or small shim. There it is. And then we'll go ahead and put our capture nut on, because we found in our analysis that we were off just a couple grams. So we need to fix it. So I'm going to lay this down.
And that's why it's important to actually weigh all the parts.
That's exactly.
If you weigh one part from the batch, there can be slight variances from part to part to part. And in this case, we're able to weigh them all, measure them, average all those, and then be able to hit right on.
Exactly. So you can see right now this one is 864.5. Now, when we put them together, it's sort of a safety or a quick check. We want to go ahead and set this up. I'm going to put this weight on here. I'm going to take this guy here. And let's see what we do with the small nut. There it is. And what we're looking for is 1729, and we're off by 1/10 of a gram.
Got to do a better job, Randy. That's slacking, man. Come on.
So all of the units will be exactly the same. And what's important, though, and I'll just, when we load them up on the unit, we use this little device right here as a known spacer. When we're on the rod journal, I want to have the bob weight set up to a known position.
Okay, yeah.
You never want to have an ambiguous alignment.
Right, so if you have a known spacer, then you could always be in the same location on every journal.
Everyone. If you don't do this, what you're going to find is the machine will misinterpret the load. Now, the machine is like a newborn baby. It believes everything you do. So the operator owns this, right?
Got it.
It's a simple issue. A lot of guys will set these things on and they'll just sort of eyeball them. Don't trust your eyeball.
Right.
Use tooling. So now we're going to take this unit here, and we're going to walk right over here a second. Let me grab one of these nuts.
Yep.
And we're going to come right up here and locate, come across, set it down. Again, safety first, and that everything that we do, taking shortcuts in the machine setup is typically a pre-accident. All right, sort of a corny way to describe that, but every time I've seen an accident is because someone's accepted the fact that they've taken a shortcut. Now it's just that simple, and off we come.
That's awesome. Okay, Randy, so we've got all the bob weights set, positioned, so now it becomes the fun part, right? We're going to spin this thing up?
Yeah, what we want to do now is find out how much energy is there. It's either positive or negative, and what I mean by that is we're going to first come in and give it a target here of 500. So it knows right now, for instance, at 0, it's not rotating. 500 is my target. I'm just going to go ahead and launch it.
Okay.
Now the unit basically will go up and it'll establish the RPM, and in doing so I'm going to get 80 cycles per side. In other words, 80 rotations, and it goes through the analysis. And bottom line is, whether you know all the mental gymnastics in the background, you just wanted to see the report, and that's what you're going to get here. Now currently On the right side, it's 42.169 grams out. Over here, 55.179. Now, what that means is at 3 1/4 inches, in other words, at the arc of the counterweight, there's 55 grams of mass that's offending the balance. Right? In other words, that's not a good thing.
Out of balance.
Out of balance. We go to the ISO calculator, and basically, this is a global machine, so we first look at pounds.
Yep.
And I want to say, well, what is this rotating assembly? And basically, it's right about 76 pounds. Okay.
Okay.
Now, the question is, what is the surface speed application? What we mean by that is, what's the peak this thing's going to run at? Well, you know, some of these drag racer guys, you know, God, they're pushing 10,000, even in some of them 11,000.
Oh yeah, definitely.
Right? So you can pick your numbers, and let's just have a little fun. Let's go ahead and put 10,000 in.
It's about to get ugly. Watch.
So now it goes in and says, what category? Now again, this is a global machine. Ounce inches is what we typically use in the U.S. Sometimes gram inches. But I'll go back here to ounce inch. And it's saying at 3 1/4, that's the radius arc, it's allowed to have a residual of 1.256 grams. So I'm going to say, okay, I want to use this. So 0.144, and say save. So you can see I'm a long ways away from this sucker.
Yeah.
A long ways. In other words, I'm 55 grams. Or in this case, 54
So
grams.
as the grams start coming down, the ounce per inch will begin to drop and get closer back to your tolerance.
Exactly.
Because this is where you're trying to get to.
Exactly.
Essentially.
Right. That's right. As an engine rotates, the amount of mass, and when I talk about this 55 grams, that is the mechanical load. In other words, there's 55 grams there.
Yep.
That doesn't grow in weight itself. It's the force that's generated.
Okay.
So in other words, if I was at 1,000 RPM, and I'm just going to say 1 gram.
Sure.
If I go from 1,000 to 2,000, that's all.
Yep.
That 1 gram is now the force of 4 grams.
Right.
Okay, so it increases with
It's
the square
exponential.
RPM.
Yeah.
That's right. It's an exponential increase. I don't want to know all this stuff. Let the machine do it. You know, it'll tell you.
Like Billy or somebody came in and did all the programming for him. So has some smart PhD guy do all this. It's probably actually Randy, but anyway, yeah. Let somebody else do the math, because Ben Strader's not always here with this calculator to do all this for you.
Well, that's the whole deal. You don't always have to run uphill all your life. You can take the nice, easy road. In this particular case, if we were sitting with a 1-inch drill, it would tell me just to make a plunge 520,000. Well, this counterweight's not that wide, so I can go in here and I can select a different drill, and let's go ahead and just put it at 625. And what it's going to do is say I have to drill a single hole 1 inch 610 thousandths. I don't like drilling that deep. People totally misunderstand that the counterweight's mission statement is twofold. One, of course, is it's out there to correct for the amount of mass of the piston rod assembly. I get that part.
Yeah.
But it is also a mechanism of structural integrity to the shaft for strength, and also for torsional load.
Right.
All right. So the torsional part of this thing, if we turn this thing to Swiss cheese, it may as well be said. What happens is the counterweight will flutter.
Yes.
Now, when it flutters, this is a bad thing because.
Oh yeah. If you were watching earlier, Guy Tripp, SoCal Diesel, went through the perils of having crankshafts moving and doing things they're not supposed to. It's a bad day. So.
This is connected to the cam. The cam is just going to respond. Now, I don't care what type of drive, whether you have a gear drive, chain drive, belt drive, whatever. There's no way you can totally sequester that. It's going to transfer.
100%. By the way, so Ed Pink, who was a guest on the Engine Expo last year, he actually told me when he was developing the Toyota midget engine, which he talked a little bit about on his segment, he told me that their valve train instability was actually from the crankshaft. Right. They started working on the front drive area because there were so many things on the front of the engine, take some mass out of that, compact it, get everything so it could be better balanced. That's what actually solved their valve train issue. So that's really interesting that you said that. And
well, not only that, I'll take it into Formula One type. Now, these are apples and oranges engines.
Right.
Let's be fair about that. Their RPM band 17,000 to 20,000.
Yeah.
All right.
Really high.
Yeah. We get crazy when we talk about 11,000. Those guys, they think of it as a turtle. You know, we got slow engines.
That's idle for them.
Right. So the deal, though, is that every rotating part that's on those engines have individual dampers. Anything that rotates, they accept the fact that they're going to have a cause and effect issue. So what they want to do is they'd love to sequester it to say it's totally canceled. That's the goal. The bottom line is you dampen it. So they have on all rotating, they'll have as much as 11 different dampers on an engine.
Right.
So now in our case, people are yelling about the fact that we're putting a damper on the end here, and they're just not understanding the principles and the purpose of that damper. Its mission statement is dampen. That's its job. But it cannot do everything. So when we come back and we balance, this is what we call first order balance.
Okay.
Now, there's a mechanical second order that's built into this, and we'll talk about that in another video, but basically what happens is if that first order, which is we're going to balance the tolerance, you got to understand, it's the one thing in the engine when it runs won't change. In other words, as an engine runs, let's say that we have that perfect cylinder wall. Let's say we have that perfect valve seat. I guarantee you, after cycle time, it will change its perspective. In other words, the ring will surrender. It'll either get better or worse, right? Same thing with the valve seat, same with the valve guide. Everything else in there changes except balance. Under no circumstances, unless you've lost the main bearing, right, that cannot change. If they do not fix that first order, right, and they put the engine together and it's vibrating, right?
It's never going to change. It's never going to go away until there's a hole in the side of the block.
Well, we get people all the time, though, that say, hey, I had this engine balanced and it's vibrating. And the first question I ask is, hey, what RPM? Well, I said, 1,000? No. 2,000? No. 3,000? No. About 3,200. Really? 3,200? And I said, what happens at 35? It goes away. Well, I just told you that balance increases with the square of RPM. So it can't be that. So what you have, a fuel delivery problem, you have an ignition problem, but the last thing you have is a balance problem.
Because it doesn't go away. If it goes away, it's not balanced.
It's not balanced. In other words, first order balance cannot change.
Okay. Now, if it's unbalanced, it's unbalanced, just like a wheel unbalanced doesn't get better the faster you drive it.
Listen, you can take it to church, you can pray for it, you can do anything you want. It is not going to change.
No.
All right. I use the term excitation and the vibration.
Yep.
If you excite metal, if you take a tuning fork and hit it, it'll resonate.
Yep.
And it has to ring out. By the way, it just doesn't go bong. It's a bong. It's back and forth. Well, this thing is continually excited. So let's have a little fun with this. I'm going to go back out here. I'm going to log in here and just see if we can bring this up. This 55 grams that we see at 1,000 RPM generates 11.2 pounds of force. Think of that as a little hammer, just for a second.
Yep.
Now, it's always going to hit the same vector, by the way. Always. Can't change. But it's going to hit 16.6 times per second.
11-pound hammer hitting the same spot 16 times per second. Ouch.
Now, remember, this thing ain't going to run for 1 second. If you're, an endurance run engine, you're running for hours. Let's move on down here and just to show you how this works. Let's move this to 5,000. Same amount of mass. Remember, that doesn't change, but the force changes. So over here at 5,000, we're 280 pounds, and we're hitting that crank at 83 times per second.
Ooh, you're scaring me.
Well, here's the deal. You have to go to the scene of the crime. The scene of the crime now is a bearing. The bearing will testify what's happening. You keep this guy going and you're 10,000 RPM.
I was murdered is what it's saying.
Well, if we go to 50 to 10,000 RPM, that's 1,123 pounds at 166 times per second. Now, if you think about it, you've seen these commercials where you got the jackhammer guy hitting the concrete. That's only 90 times per second. Okay. That's with a 125 pound hammer. I've got a 1,000-pound hammer hunting 166 times.
Wait a second. A jackhammer is 90 times per second at 125 pounds.
Right.
All right, I'm trying to find that on the list here.
That's just it. You can't even get there. If we get back and we're back here and we said 90 times per second, we'd be right here at 5,000 or 280 pounds.
Yeah.
I'm already 2.5 times plus what that jackhammer was. Now, the hydrostatic event that the bearing lives in, it's the catcher's mitt, right? It'll surrender, and here's why. I can go ahead and hit something once, I can hit it again, but now all of a sudden I just keep it, and then we have a Bernelling effect.
Yes.
Right? Even though it's a hydrostatic event, what we're going to do is we're going to deform the housing. The bearing is going to surrender to the roundness, and at some point, oil seeks the avenue of least resistance.
Yep.
If it can get away from load, it'll run away from load. What's important here to understand, especially when we talk, people call me a lot of times, they say on the bearing just wiping. See, just right on it. They say, what's wrong with that? I said, well, you're making more power than the crank can stand. They said, what? I said, basically, that crank is doing
bending,
this. Right there. And so you're at the apex of that bend. So you get the swiping on the bearing. And so I used to get these calls, especially at PRI, that people would come to me and say, well, how do I fix that? Lower your horsepower. And I said, are you crazy?
Yeah, no one wants to do that. Yeah.
That's off the deal. So I said, look, the bottom line is you have the next choice, increase your structural strength. Better crank, alloys, radius, whatever you're going to do there.
Well, the different bearing alloys, right? That's part of the bearing design is they've got different alloys or material compositions to try to have more strength to be able to withstand the load.
Exactly.
But I have a suspicion, though, what we're trying to do here is take away that hammer.
That's right.
And,
That's the first part.
And slow down the pace.
Look, if we get this thing down, and we'll show you this report at the end when we balance this crank, we're going to get down to where we're only sitting at 10,000 RPM with about 5 to 7 pounds of force.
All right, that sounds better. I'm not scared now.
Now, that's right. And so the bearing and the design is meant to handle it.
Kind of picking up on that, that's a difference between, hey, crank flex is different than imbalance.
Oh, absolutely.
So crank flex can be, hey, I'm making 10,000 horsepower. I've got so much cylinder pressure that it's actually forcing the crank to bend. That's different than being out of balance. And so what we're trying to do here is fix what we can fix, which is...
Every good engine builder minimizes or eliminates variables.
Yeah.
All right. That is the total focus of a quality engine builder. But balancing is critical to be part of that. In other words, you're taking that variable completely out.
It sounds like if you don't balance, you're letting Murphy into your engine and you gave him a hammer.
Oh, yeah.
And you don't know how big the hammer is, but you know he's going to be banging on it a lot. So it's just a matter of time before Murphy hits it in a crack. So yeah, I think you're right. It's
the hammer. I'm glad you use that because I use this analogy a lot. I say a little baby with a little hammer stuck in a room by himself, no attention, will destroy that room. That's what unbalance does. It is that little bit. It's not something, but it increases exponentially with the RPM. And so what it will do is it'll attack everything from oil pan to the wing nut. Yep. It affects it.
Okay, Randy, so taking the crank, back in the shop.
Right.
Made some chips. They were probably really small chips because you didn't use a drill this time.
No, a lot of people, we do drill as a quick correction. Because of this application, there was already previous holes from the factory.
Right.
So what we decided to do was put it in the crank grinder and actually set it up in an elliptical grind. So we just went ahead and ground the counterweights down by removing the weight. There's two ways to skin this cat. Well, one is drill, the other one's grind. First of all, if I ever had the opportunity, I would have no holes, period. End of story.
Okay.
But given the fact that this is a manufactured crank that they've already
had holes.
Yeah, that's right. So we said, okay, do we want to add more holes? And the answer is no. If the counterweights themselves become flexible, they become excitable, and so they quiver.
We don't like that.
God, we hate it.
Yeah.
All right. This is one of the things that really, once this thing becomes nervous, if you will, and I'm just gyrating right here, I can tell you everything related goes stupid. So we want to stay away from that. We want to ensure that the minimal amount of material is removed that gives us the best structural integrity. This is the grind area here and the grind area here. Now you notice it's not perfect, so we had to offset it in order to maintain what we call a couple. The bottom line is that's on this end, and then of course we have it here on the other end. It's exactly the same. Now the end result is we remove the offending mass, the unit is then couple, and we're within the standard of our balance. So this is a finished job.
So cool. So this baby is ready to go to Jimmy and the guys over at Yates so they can go ahead and start putting the short block together. Okay, Randy, so you've got the balance done.
Right.
But let's show how much has changed, because earlier we had this crazy guy, Murphy, running around the engine with a big giant hammer that was, 280 pounds, like double what a jackhammer was, moving at the speed.
Right.
So what have we done to Murphy and his jackhammer now?
Well, the bottom line is we basically tamed him.
I like it.
We had all this event, like I say, real quick. We had 55 grams on the left. We had 42 grams on the right. What's important to understand that mass stayed the same during the entire RPM. Now, that's the physical weight. It's important you understand that doesn't change. But the energy generated, right, the centripetal load. Now, at 5,000, let's go out here and you can see that too. I'm going to move down to our finished job now on the left. This unit now is down to 0.15 grams. Right, and then we're sitting there with 0.808 pounds. We're still hitting at 83 pounds per second.
You went from a 280-pound hammer to a less than 1 pound hammer.
That's absolutely right.
That's pretty impressive. That's just grams we're talking about. Grams, not pounds.
Right.
Grams. That's okay. Yeah.
Well,
I was scared earlier. Now I feel better, but I'll be cautious from now on about this because this is serious.
Well, again, to not balance an engine, well, I have to go back and challenge your intellect. I have to ask you why in the world you wouldn't do it after we've demonstrated how grams turns into 1,100 pounds.
Yeah, that's really significant.
Sure.
Grams into 1,100 pounds just add speed, and of course that's what we want to do. So this is a great lesson. Randy, thank you so much for taking this time to enlighten us about this subject. You're going to be around, right, to answer questions and stuff. So you got any questions, put them in the chat box, comment. Let's talk about it because this is cool stuff.
Studio here at the Engine Performance Expo. Lake and of course Randy back. If you've got questions, now is the time. Randy, the little baby with the little hammer smashing inside the engine. What a great visual, but it works.
Well, the purpose of that is, again, to try and get people to have some sort of visual reference, but as we've shown in the previous video, that little hammer turns into an 800-pound gorilla. This guy, if you leave these things alone, this little thing that we start with turns into a major contender in that it's literally just pounding this thing, but at a much accelerated sequence. In other words, we're going from maybe 8 hertz, meaning 8 times per second at 500 RPM, 10,000, that's 166 times that 800-pound hammer. Man, it's going to do some abuse.
Well, the thing that really stuck with me is that it doesn't fix itself.
No.
If it's there, it's always going to be there. It's not going to get better. It's not going to wear itself in. If it's wrong, it's going to be wrong and continue to be wrong. And the higher the RPM you go, the worse it gets. It finally kind of clued into me after we did the video. It's like, oh, this is what Billy's been talking about on Valve Train forever. We kind of understand it. Oh, the higher the RPM you go, the more dynamic forces there are. Well, guess what? It can be in your crankshaft too, but at least in this case, you can control it.
Well,
you can eliminate it, whereas the valve train, you've got to manage it. This case, you can eliminate it.
Well, if you don't do this, let's be very, very clear. Whatever you leave parasitic is you can't get rid of it. That's all there is to it. And people are treating this with a very cavalier attitude. Listen, once you take this up to the point that the damage says, or the bearing says, ouch, I'll say, okay, I'm Superman, I can heal myself. It's done. All right, everything from that point on is degradation. So it's a critical part of the equation that we overlook in the industry, but yet I got to tell you, you talk about finding that parasitic loss or that durability dynamic. If you overlook this, you're headed for a train wreck. End of story.
Well, the thing you were talking about, and I know from the Formula One engines, we had that one little clip from the video of the Cosworth DFV. That all those things were all gear drives, and it's a 14,000 RPM engine.
Right.
But they had all these dampeners built into it to basically take that out because they knew you couldn't have durability at that kind of RPM if you weren't balancing and dampening pretty much everything.
In the old days, there was a song by Tennessee Williams, the knee bones connect to the shin bone connect to the ankle bone. Let me tell you something. Especially when we had that visual, look at the linkage. Mm-hmm. Now, it starts here, but it ends up there. Right?
Right.
Now, and there's no way to in the middle say, caught it, parking our way. This thing's okay. Wrong. Yeah. If it's excited here, buddy, it's excited there.
Right. I mean, I think back to some of the stuff we did at Joe Gibbs' NASCAR part. There was one time there was an engine configuration we had, and we had aluminum rocker arms on the car. And I'm like, why in the world do we have aluminum rocker arms? And it was because of that. There was excitation somewhere else in the engine, and the only way to keep the valve train alive was to dampen it, cushion it by doing that. So that was really should have been the red flag. There's a problem somewhere. Yeah. We got to find it.
All right, we got a quick question from Jason out there. Just to dive in. He says, distance to grind, or was it grind a little and respin it? And that's a follow-up to, does the program tell you how much to grind off the counterweight, from Jason?
Yes, it does, but it's also not magical. In other words, it gives you a general understanding of whatever the shape is, but if you got a million holes there already, I can't see that, nor can the program.
Right.
But it is a great great starting point as opposed to guesswork. Guesswork sucks. Okay.
Yeah, so
Guesswork
follow what it says,
Oh.
respin it, and then you'll just get right there.
It's the math. You want to try and beat it? Nice try. You're not going to win.
All right, we got another one. Gerald, we got a bunch of questions for you, Randy.
Okay.
Engine overbalance and underbalance, what's your opinion?
There's a webinar I think you did on that, right? We could be here all day.
Yeah, I need 10 hours. Let's just simply say contact me. I'll be more than happy to visit with you. I got to tell you, there's a lot of misnomers in there, okay? And we're anxious to clarify that.
Yeah. Maybe it's a future segment, I think, maybe.
There you go, absolutely.
And Rick's been out there watching throughout the day. Actually had a question about engine honing, and but he now has a question about balancing. So he's like engaged, and we appreciate that. We'll get back to the honing question because we're going to do a little more of that later. We got Randy. So if I had a balanced engine and had to change a component and added 10 grams to a piston, what kind of change in force would we have? Any idea? That's kind of
Bad force. There you go. And let's keep it that simple. You can't tell me you're going to do 10 grams and expect it to get better. Nice try. And a lot of the engine builders will go ahead and pass through that. Now, you got to get back to basics. Math is math. Follow that. Don't entertain yourself with a falsehood.
Well, the 10 grams is going to be more impactful the higher the RPM of the engine.
Listen, it's not a single answer here. And again, call me. I'll be glad to visit. But let's understand, once you start putting guesswork into this equation, you're going to get penalized. End of story.
There you go. CWT, children with toys. And of course, Randy, the little baby with a hammer. We'll see you back in a little bit. Thank you so much,
Thank
Randy.
you so much, buddy.
What a day, what a day, what a day. Yeah, my brain is swollen. I've learned so much today. They told us, don't start cars. We are not going to listen.